but hopefully it will still be interested for the main audience here. And I'm talking about congruence defined for words, Simon's congruence, and how you can efficiently test this congruence. And this is work that I did together with Paweł Gawrikowski and my PhD students Maria Kosche, Tore Kos, and Stefan Zimmer from Göttingen. And yeah, basically the concept that I'm going to talk about is a very basic and simple concept. It's that of subsequences. So if you have here a word, a subsequence or a scattered factor is a word that can be obtained from your original word by simply removing some letters. So here you have a ton of subsequences of this word. And for instance, take A, B, A, B, A. This can be obtained, for instance, by removing B, C, and so on. So you read it A, B, and A here. So either you want to remove some letters and obtain your subsequence, or you just want to read the subsequence by, jumping from one letter to another inside this word, always going from left to right. Now, for instance, ABC is also a word, but it's not a subsequence of this initial word that we have W, because you cannot find A, B, and C while going from left to right in this order. So for instance, you find A here, then you look for a B, you find B here, but after this B, there is no C. And as you have seen, I identified this, or I tried to identify this subsequence in a sort of a greedy manner. So I took the first A, then I took the first B after the first A, and this should be enough. If there is a C, I should be able to find it in this way. So if ABC would be a subsequence of W. So ABC is not a subsequence. All the others that you can see on this slide are actually subsequences. You might also know subsequences as scattered factors. Sometimes I think that they are called this way. We went for the subsequence name because I think this is more of the usual name when you look at algorithms for this kind of scattered factors. So a formal definition is pretty easy to see now. We call W prime a subsequence of length k of a word W if there are some positions I1, I2, Ik of the word W such that W prime is exactly the word that can be obtained by reading the letters on the positions I1, I2, and so on up to Ik. And here you can see like a drawing what that means. These I1, I2, and I3, they don't necessarily need to be consecutive. They can also be consecutive and so on. Obviously, if ij plus 1 is ij plus 1, then, so basically all these positions are consecutive, then we talk about a factor of the word, which, are also a well understood and very interesting notion, of course. Now, the set of subsequences of length k of the word W is defined as subsec k of W. And in this particular talk, we will make a short, difference, and we will talk about the subsequences that start on position I of the word W. So basically, subsec k IW will be the set of subsequences of length k of the word considered from the position I on, so to the right of position I, including position I. And obviously the subsequences of length k of the entire word W will be denoted simply by subsec 1W. And if you want an example, consider the word ABACA, and the subsequences of length 2 of ABACA are obviously AA. You see A here, and so on position 1 and on position 3. Then AB, this is also a factor occurring on position 1 and 2, AC, and so on. So these are all the subsequences of this word here of length 2. Now, this is a fairly clear and well-known concept. Now, I will move on and define the main concept of this talk, namely the Simon's congruence. In this case, we take two words, W and W prime, over the same alphabet, and we call them Simon equivalent, or equivalent under the Simon's congruence sim k, if they have exactly the same set of subsequences of length k. This is how this Simon's congruence is defined. Basically, if you look at the Simon congruence of sim1 for k equals 1, this just says that w and w prime have exactly the same letters. And in this case, we talk about subsequences of length k. So basically what's going on here is that, so what's maybe good to notice is that we are essentially just discussing about sets of subsequences, so not about so we don't look at multiplicities, right? We just look at the sets. It doesn't matter if a letter occurs multiple times or if a subsequence occurs multiple times in W and just once in W prime. It's important that these sets are equal. So let's again look at two examples, actually several examples. Consider these two words here. If we look at the subsequences of length 2 of these two words, actually you can check that they are identical, so these two words have exactly the same sets of subsequences of length 2, and this means therefore that they are sim2 equivalent. And again, if we take the same letters, we see that, for instance, BBB is a subsequence of the second letter of the second word. So you see it comes first position, and then here before the last A we have two B's. So in the end, BBB is a subsequence of W prime, but BBB is not a subsequence of W. So this shows that basically these two words are not sim3 equivalent. Now, once we introduce this congruence, we can maybe define some prerequisites, some technical prerequisites that will allow us to work with this congruence later. If we consider two positions of the word, we can define extension of the Simon's congruence for these two positions, of course, with respect to the word W, where we say I and J are K equivalent if WIN and WJN, so the suffixes starting on position I and J respectively, are sim K equivalent. And yeah, we say that these I and J are K equivalent. And the word U of length K is said to be a distinguished word for W and W prime with respect to the Simon K equivalence if U occurs in exactly one of the subsets of subsequences of length K of W and W prime. So for instance, in the example that we saw before, if I go quickly back here, this BBB was a distinguishing word for the two words W and W prime. And now we can get to the basic two problems that we will approach. I call them SimK and max SimK. The first problem is just a decision problem. Given two words, ST and a natural number K, we need to decide whether S and T have exactly the same set of subsequences of length K. So is S SimK equivalent to T? But pay attention, S, T, and K are given in this case. Max SimK is the associated optimization problem. So given ST, we're not given any K this time. Instead, we want to find the maximum K for which S and T are K equivalent. So obviously, it seems kind of natural that the first problem should be at least at a certain level simpler than the second problem. And yeah, so these are the two problems that will be the main topic today. The line of research dealing with these problems was originated, so started in the thesis of Imre Simon in 1972. This was a thesis that I think he did under the supervision of Janusz Brozowski at Waterloo. And basically there he defined this congruence, which now bears his name. So the Simon congruence was introduced in Simon's thesis in 72 as a tool in studying K piecewise testable languages. And already in that thesis, I think that basically the problem of whether max SimK and SimK can be solved or in linear time or as fast as possible. So the algorithmic problem of solving these two, so basically the question of solving efficiently these two problems was asked. So there was a long history of algorithm designs and improvements for both these problems and related problems. I think that the state of the art about 2 years ago, so when I started looking at these two problems, was the following. Kufleitner and Fleischer at MFCS 2018 had a very nice paper where they showed that essentially you can compute the short lex form of a word. So that's the shortest word and lexicographically smallest, which is equivalent to a given word from the point of view of SimK. So they showed that this short lex form can be computed in linear time for constant alphabets. So constant alphabets means that you know that your alphabet is, so the size of your alphabet is bounded by a constant. So let's say has at most 4 letters. Now, obviously, it's interesting what happens with these problems when you consider larger alphabets. Like, for instance, assume that your letters are integers, upper bounded by, say, the length of the word. So if your word has length n, then the letters of the word are integers between 1 and n. This is not an outrageous, assumption, because basically, if you consider how characters are usually encoded in computers, they are an integer type. And in all programming languages, or in most of them, characters are integer type. So it makes sense to try to solve your problem for integer alphabets, so unbounded alphabets, rather than assuming from the beginning that you have a constant size. So at DLT 2020, with Pamela Fleischmann and Dirk Nowodka and some of their students from Kiel, we have shown that basically SimK can be solved in linear time for integer alphabets. This basically was not something, super original. We just took the paper of Kufleitner and Fleischer, and we used some clever data structures to compute these short lex forms. So we used essentially the same algorithm, just that we were more careful with the time management and basically the data structures that were used there. And however, max SimK, even with these two, results, could only be solved in n log n, because essentially what we were able to do is, once we know how to solve SimK, then we can binary search for the value of K. So what's the biggest K for which two words are Simon K congruent? And that was a bit disappointing, because in a paper, I think it was an invited paper or an invited talk at Words 2003, Simon claimed that there is a linear time solution for max SimK. This solution was never published, and I'm actually happy I saw that Maxime Crochemont was here earlier. He also said that he never saw this solution, so it was not only us that we didn't find it. I think that basically it might be that Simon had the good idea. It wouldn't surprise me, because I think his work is brilliant. So generally, it wouldn't be surprising that he actually had a linear time solution for max SimK, but it was never published. And also, we were not able to extend his ideas from this paper from 2003 to obtain this solution ourselves. So a natural question was, is max SimK actually linear time? Was Simon right or not? And today I will present you a confirmation of Simon's claim. So Simon was right, and this is not surprising, but now we also see a linear time algorithm for this problem. And basically this is, so now the main part of the talk starts, and I will present you the results that we have in this paper, which will be also presented by Maria Kosche and Tore in 2 or 3 weeks at STACS 2021. So the idea that we had in solving this problem was to introduce a new data structure, which allows us to work nicely with these classes, with this Simon congruence, so the K-sim or sim-K as we call it. And the idea was that we should split a word with respect to the suffixes into blocks of equivalence classes with respect to sim-K. And this works because if you have two positions of a word, I and J, which are sim-K equivalent, then every position between them, so for instance, I is equivalent to J, and then you take some L between I and J, then every position between them will also be sim-K equivalent to both I and J. And if you define this, this splitting of a word into blocks according to this relation, you actually see very easily that the blocks that you obtain for sim-K plus 1 are essentially a partition of the blocks that were obtained for sim-K. Obviously, because sim-K plus 1 is a refinement of the sim-K relation. Now, an index I or a position I is called a K plus 1 splitting position if I and I plus 1 were sim-K equivalent, but I is not sim-K equivalent to I plus sim-K plus 1 equivalent to I plus 1. So basically, these are consecutive positions that were friends up to level K, and suddenly they decided to split at level K plus 1. And using these basic definitions and properties, we can actually compute these blocks of a word, and essentially the blocks induced by the sim-K relations for K from 1 on inside a word. So I and J are sim1 equivalent if and only if the alphabet of the two suffixes defined by I and J are equal. So the two alphabets are equal. And now this holds obviously for all I and J. So this is how you decide if two positions are equivalent. And now what you can do, you can just go from right to left through the word and keep some sort of characteristic vector or counter for the occurrences of all letters, and essentially decide whether this holds. So see how the alphabet of various suffixes varies. Obviously, the alphabet always grows when going from the right to the left. So you just need to see when the alphabet of a certain suffix changes, so when a new letter occurs. And this is how you can actually define the blocks for K equals 1. And if you look at this example, here you have the word BAC and so on, BAA, BADA, and you go from left to right. Obviously, you start a new block with A, then comes D. This is a new letter, so a new block starts. Then you get an A. This occurred before, so this doesn't change the block structure. Then there's a B. This is a new letter, starts a new block, and this block extends all the way till we meet a new letter, which is C, and then this is the last block of the word when you go from right to left. Now, when you consider, so basically these are the 1 blocks. Now, when you consider K blocks, or actually K plus 1 blocks for K greater or equal to 1, the way to compute these blocks is pretty similar. The only thing is that you need to localize on the 1 blocks and apply the same reasoning. And yeah, essentially the idea is that the K plus 1 blocks are obtained by going from right to left through the word without the last letter. So now I will consider blocks, and I always do not care about the last letter. This is a sort of technical property. And then you just determine the K plus 1 splitting positions exactly as you did for 1 splitting position. So for instance, if you consider this middle block, now you start after this splitting position, so to the left of this splitting position, and you see an A. This is a new letter, so we will have a block splitting after this A. Then this A is not a new letter, and so on. So basically, you will have A and B, the new splitting positions. Once again, B counts it as a splitting position because we neglect this last letter of each block. And this is the splitting in 2 blocks. And you see both the splitting positions, which are here below, and the blocks themselves. And finally, you can do the same and obtain the 3 blocks. And that's it. Obviously, for such small words, this is, once K becomes quite large, they also become very fragmented in blocks. So this is how you compute the blocks. This is what we defined so far. Now we can define a tree which helps us represent these blocks. So we have a new data structure, the Simon tree. This represents the block structure by, the blocks on level K have as children the blocks on level K plus 1 in which each of these blocks is partitioned. And it also can be, allows us to efficiently manage these blocks and the positions of the word. And nicely, it can be constructed in linear time. So for instance, for the word that we have seen, this is the Simon tree that we see. You see here, you have the 0 block. Obviously, that's the entire word. Then here you have the 1 blocks, and here you have the 2 blocks. Obviously, if a word was already a singleton, so a block was already a singleton on level K, it will remain a singleton on all the levels below, and we don't need to, copy it over and over again on the previous, subsequent levels, because, well, it will just be inefficient. And yeah, that's essentially the partition of the word here in blocks for K. Now, how do we actually construct this tree and how do we actually define it? Well, the definition is kind of straightforward. The Simon tree, TW associated to the word W, is an ordered rooted tree. The root corresponds to the 0 block, and then for K greater than 1 and for a node B on level K minus 1, which represents a K minus 1 block, the children of B are exactly the blocks of the partition of IJ in K blocks, ordered decreasingly by their starting position. For K greater than 1, each node on level K minus 1, which represents a K minus 1 block II, is a leaf. So as I said, once a singleton, always a singleton. It doesn't change. I won't copy it. I will just consider these nodes as implicit on each level, greater or equal to the level where they became a singleton the first time. The construction is kind of nice. It resembles pretty much to the construction of the Cartesian tree for a set of points for those who are familiar with this data structure. The idea is that we build the Simon tree right to left as the word is traversed right to left. So we kind of always update the Simon tree for a suffix of the array. And the benefit in doing so is that we always affect only the leftmost branch of the word when considering a new position. And the idea is pretty easy. Insert a new position letter into the tree by moving up to the on the leftmost branch from a leaf towards the root. And we find on this leftmost branch the lowest node, which is not split by this position, and we close all the others on the way. So we decide that they are blocks which we completely identified and close them. And then once we found the node that it is split by this position, this is a splitting position, so we insert a new position. Once we find a node which is not split by this position, all the nodes below were split by this position, so they were closed. Once we found this node, we simply insert this new position as the leftmost child of this node, because what was below this node was already closed. So let's see an example. For technical reasons, we will use this extra character $, which is a character that does not appear in our word. And if you look at the word, we start with this, then we have an A. Now this is on level 1. It's really easy to split on level 1. This is a new letter, so we create a new block and we close the block that corresponded to the $. Now you have a D. This is also a new letter, so we will close this one. And because if we would add it here, it would lead to a split. We end up with this node and we start a new block. Now comes an A. This doesn't split on, so we go up the leftmost path and it would not produce a split on level 1 by the rules of computing the splitting positions on level 1. So we add it as the leftmost child of the node which was not split, which is this 9. And then comes a B. A B is a split here, is a split here, and essentially it becomes the leftmost child here, and so on. So basically, we can, maybe here it makes sense to consider this case when you have a B, it would produce a split on level 3, it will produce a split on level 2, and if it goes on level 1, then again we apply the rule for splitting positions on level 1. Here B occurs to the right of this position, so it will be the leftmost child of this node, which is not split, and so on. Basically, we can do that up to the last letter, and then we also finish the construction of the Simon tree, and then we can remove the dollar, and there you go. This is the Simon tree of the word. So the Simon tree can be built in this way. The complexity is linear because it always, it's an amortized argument. All nodes appear only once on the leftmost path until they are closed. And this ends the discussion about this data structure, but this is only for a word. Now, given 2 words, we want to find the maximum k for which they are equivalent. What are we going to do? We are going to set these 2 words in relation, one with the other one, by using their respective Simon trees. And how do we do that? We transform these words into Simon trees, as shown before, and we use this tree structure to connect equivalent nodes of the 2 words. And the first, the important thing that we define here is the so-called S connection, which basically says that the nodes, 2 nodes, A and B of these 2, respectively 2 trees, are S connected if and only if the suffixes that corresponds to this node are k equivalent for all suffixes that occur in these 2 blocks. And this is hard to build this as connection directly. So we will define an over approximation of this connection, the so-called P connection, and then we will just refine it iteratively till we cannot refine it anymore, and then it's at that point we have reached the S connection. So essentially the P connection is very simply defined. The 0 nodes of the 2 nodes are connected, and then for all levels, if A and B are connected on level k, then the ith child of A is connected to the ith child of B when counting from right to left again, and no other nodes are P connected. So here you see with the same color, we have the nodes which are P connected. So basically dollar to dollar, A to this B, and so on. And yeah, basically, for instance, look, this A has only 1 child. Now this node, which is connected to this A, also has, actually has 3 children, but the child of this node is only connected to the first child of this node in the other side. Now I did a trick.
Sorry, Florin, I'm really sorry. You have a couple of minutes more, but not more.
I know.
Sorry.
So I will hurry up. Basically, what I wanted to say here is that I did a trick. So I also made an extra copy of these singletons so that every node is connected to something on the other side. So yeah, essentially, the question is how to refine the P connection. And here we defined a relatively easy way to define it. So we defined a property which tells us when 2 nodes can be split. So 2 nodes are not equivalent on level k plus 1, if and only if there exists a letter such that when starting with, exactly after that letter in S and the first occurrence of that letter in S and T, the first occurrence after these 2 blocks, we obtain 2 suffixes which are not equivalent on the previous level. And this actually allows us to, once again, look at the nodes which were P connected and identify nodes which are no longer P connected. Maybe these 2 are interesting. You see, here we have an A, here we have a B. So these 2 nodes were P connected. And now we look for the first occurrence of a letter after this block in the left-hand side and the first occurrence of a letter after this block in the right-hand side, and we take the A. Here we have an A, here we don't have any A. So obviously these two nodes cannot be connected anymore, and so on. So essentially we will just identify the nodes which are not connected, kill them, so kill the connection between them, strike it out. And what we obtained by just, getting rid of these nodes which were p-connected but not s-connected. In the end, we obtained the true s-connection. And now we just have to look what's the last level on which the first positions of the two words are equivalent. And this is k equals 3. And these, actually they were not equivalent. Sorry, that was k equals 2. So you see here this yellow node and this yellow node here are still connected. So basically the answer to our optimization problem will be k equals 2. The solution, the last level k, where the k blocks containing position 1 of the input are equivalent. This gives us a way to solve maxim k. The distinguishing word can also be obtained. And this, nice structure that we always have an interval which we split and find and do some find operations in it, allows us to employ some interval union find and split find data structures which work in linear time. And this allows us to do all this, P connection and S connection management in linear time. So the problem can be solved in linear time. I hope I convinced you somehow that this holds, and I also hope that you will read this paper. Just a quick thing as future work. Now that we know how to test k equivalence, the question is, how far are two words in order to be, from becoming sim-k equivalent? And we also, so this is a kind of natural problem, but it seems also very hard to us. And we have started to do some first steps in this. We have a paper again at Stux 2021 about the edit distance to so-called k subsequence universality. But the general problem still remains open. Given two words, how far are they with respect to one of these classical distances, edit distance, Hamming distance, to become sim-k equivalent? Sorry for being late, and thank you for your attention.
Thank you. And maybe just a very quick question, because we are indeed a bit late. Sorry.
So I think that Maxime has a question.
Hello, Florin. You hear me?
Maxime. Yes.
Okay. How is your Simon tree related to the minimal automaton accepting all the subsequence of a word?
I actually did not look into that, so the answer is I don't know.
No
Sorry,
worries.
I know that. No. So I'm aware that this was an approach that you and one of your students did at some point try to solve maxim k with, but I didn't investigate this relation. I think it's a good question, so I will look into that. Sorry for not having a better answer.
No worries.